So in some of the last sessions, we talked about the properties of the thermal radiation spectrum or the black body spectrum, where if I have a solid, a liquid, or a dense gas, then if that material has a certain temperature, it's going to give off a certain thermal spectrum, a certain spectrum of light. Again, these graphs are looking at the brightness of the light on the vertical axis and what wavelength you're looking at in the horizontal axis. And the properties of those thermal spectras were, if the temperature is increased, first you give off more light overall. The object is going to glow more and more brightly the higher the temperature of the object. And the peak of that graph, the wavelength of maximum emission, is going to go to shorter and shorter wavelengths as the temperature increases. Higher temperature, there's more energy in those molecules that are vibrating around, so it's going to produce a greater proportion of light with higher photon energies, which again corresponds with shorter wavelengths. But when we looked at the features of the sun, we saw it had that kind of general shape to it, but there were a lot of other features in there as well, all these like little spiky parts in that spectrum. And that's what we're going to be talking about today, the properties of spectroscopy. So in order to talk about this, again, we're going to be looking at a bunch of different kinds of systems to see how these spectra are produced. So for example, if I'm just looking at a solid, liquid, or dense gas, it's going to make one of these thermal spectra that we talked about, one of these continuous spectra. However, if there's a cloud of cooler gas in front of that source of light, that cloud of gas is going to absorb certain wavelengths of light. There's going to be if you look at this through a spectroscope, you're going to see a rainbow of colors, but it's missing a few dark bands. And those wavelengths of light that this cloud of gas absorbs, it's going to re-emit those wavelengths of light in different directions. And we're going to talk about each of these kinds of spectra, how they're produced, and what the specific special bands of colors of light tell us about these clouds of gas. So before we get into the weeds on this, we do have to talk a little bit more about the properties of atoms. So we said our general model of an atom was in the nucleus, we have the protons and neutrons. So protons and neutrons in there. And around the outside, we have these kind of clouds of electrons orbiting around it. But the point that's going to be very important for right now is that these electrons, as they orbit around the nucleus, they're only allowed to be in very specific energy states. So if we were to draw these electrons going around the nucleus of the atom, we could draw something like this, and then there's another energy level here, and another energy level here. And you could draw more and more of these different possible energy states. So an electron that's orbiting around this atom, it can be in any one of those states. There are restrictions on how many electrons can be in each state and some properties there that we're not going to worry about too much. But basically for now, the key point is an electron cannot be between two energy states. And depending on exactly what kind of atom this is, if it's an oxygen atom or a carbon atom or a certain isotope of iron, which energy states are there is going to depend on exactly what kind of atom it is. Now, when we talked about the continuous spectrum, we said we're dealing with a solid, a liquid, or a dense gas, where all the molecules, or I should say all the atoms, are really kind of closely bunched together. And in that higher density environment, these electron energy levels can change a little bit. But for now, for this portion, we're going to assume we are dealing with a low density gas. So for this part, we're looking at specifically low density gases. And these gases, in these low density gases, again, the electrons are only allowed to be in very specific energy states, and each of these atoms are basically going to act completely independent from each other. They aren't going to affect each other. And we're also going to assume that, at least for now, each electron is confined to its own atom. So the electrons can't jump from one atom to another because, again, this is a very low density gas. So that's going to be less likely to happen. So when we look at the electrons in each of these energy levels, if I have an electron in a low energy state, and it wants to move up to a higher energy state. Maybe the electron starts down here. Maybe the electron starts down here and wants to jump to a higher energy state. Or maybe I have an electron in one of these higher energy states and it wants to jump down to a lower energy state. If an electron wants to change which energy state it's in, it has to do that by absorbing or emitting the right amount of energy. And it's going to do this by either absorbing or emitting a single photon of light with just the right amount of energy. So let me write that down. If an electron wants to change levels, it has to either absorb or emit one photon with just the right amount of energy. So if electrons want to change states, they need to gain or lose the right amount of energy. And again, they're going to do this by either absorbing a photon, if you're going from a low energy state to a high energy state, or by emitting a photon, by going from a high energy state to a low energy state. So again, the electrons must absorb or emit single photons of energy corresponding to the difference in these fixed energy levels. So I think a numerical example, I'm not going to focus too much on the numerical side of this, but I think a numerical example will help make this point. So let's say I have a particular atom and it has some different energy states. So we have the energy state, and we're going to call the lowest one 1, then 2, then 3, then 4, then 5. So we've got these different energy states. And this diagram is just kind of representing, the lowest energy state would be this lowest rung around the atom. Next highest state would be the next rung around the atom, and you could go on more and more from there. Each one of these states corresponds to a very specific amount of energy that the electron has. We're going to use this energy unit called EV, electron volts. It's not important what that physically corresponds to right now. Just say for now, it's some unit of energy. And these energy states, for reasons that, again, I'm not going to go into too much, we always describe these as negative. But let me just kind of make some arbitrary. So let's say this is negative 15 EV. Let's say this is negative 12 EV. Let's say this is negative, 7 EV, negative 6 EV, and then negative 2 EV. I don't know. I'm just making this up. So these would be the potential energy states of some hypothetical atom, of the electrons around that hypothetical atom. And let's say I've got an electron that's starting in some energy state. Typically, if left on their own, electrons are going to be in the lowest energy state possible. So let's say we've got an electron starting down here. And that electron, let's say it wants to jump from the first energy state to the third energy state. It wants to jump from negative 15 EV to negative 7 EV. Well, in that case, it needs to absorb just the right amount of energy in order to make that jump. So if we have a photon of light come in And if that photon of light has just the right amount of energy, let me actually label it coming in and hitting this electron here. In this case, if we're going from negative 15 eV to 7 eV, that means this photon of light has to have exactly 8 eV of energy. If it has 8 eV of energy, it's got the right amount of energy to kick this from negative 15 to negative 7. Let's look at a different case. Let's say we had this electron starting in this bottom state, and a photon came in that had 3 eV worth of energy. Then what do you think might happen to this electron? Where is it going to end up if it gains 3 eV worth of energy by absorbing that photon? Well, if we're starting in this negative 15 eV state and we absorb 3 eV of energy, well, that'll kick us up to that second energy state. So in that case, it's going to be able to absorb that photon. So this one, it likes to absorb 3 EV photons. It likes to absorb 8 EV photons to get the jump up here. There's other jumps that you can kind of go through and see what it would do. But let's try another case. Let's suppose a photon came in this case, with an energy of 5 EV, or let's say 5.5 EV, just to make it very clear. Well, if this electron tried to absorb that photon, it's going to be somewhere in between these two states. It's not going to land in a final energy state that's allowed for this particular type of atom. So this photon that's coming through here with a certain amount of energy, it's just not going to be absorbed by this electron. That one will not be absorbed. That one will just fly right through the atom and be completely unaffected. So I'm hoping that this diagram shows that there are certain energies, certain photon energies that this atom is going to want to absorb, and other photons that have other energies that could come by and it would not want to absorb. This atom would not want to absorb those particular photons with those particular energies. So if we're going from a low energy state to a high energy state, it has to absorb some energy. On the other hand, let's say I had an electron that was starting up here. Let's say if it was already in an excited state, and this electron wanted to drop back down to the lowest energy state, to that energy state number 1. It starts out with an energy of negative 7 eV. It wants to get down to negative 15 eV. So in this case, in order to do that, it has to emit a photon. And what's the energy of the photon that it has to emit? Well, it has to do these transitions using a single photon. It can't be a combination of photons. Each time it jumps between states, it has to land on a specific state. So if we're jumping from the third level to the first level, that's going to have to emit an 8 EV photon. So this particular atom is going to be pretty good at emitting 8 EV photons. Similarly, if we had an electron in this second energy state and it dropped down to the first energy state, it's going to do that by emitting a 3 EV photon. So it's going to be good at emitting these 3 EV photons if we're starting at a high state and going to a lower state. You can kind of look at this graph and say, would there ever be a situation where this atom would emit a, let's say, 2.5 EV photon? Oh, are there any transitions where I could go from a high state to a lower state, and the difference in those energies, the amount of energy that needs to be expelled, do we have any of those situations where 2.5 EV of energy fits that requirement? There are none of those drops, so this atom would not emit those particular kinds of photons. So a couple of really important points here. If we're going from a low state to a high state, we need to absorb a photon. So for the electron going from low state to high state, the high, that's going to have to absorb a photon. For the electron going from high to low, that's going to have to emit a photon. And again, depending on what atom we have, and depending on the spacings of these electron energy states, these atoms are only going to like to absorb and emit photons with very, very specific kinds of energies. Another important point is that the energies that it likes to absorb are always going to be the same as the energies that this atom likes to emit. So the energies of absorbed photons equals the energies of the emitted photons. Again, another quick example, because I think I did all these transitions with the first level. That doesn't always have to be the case. Let's say I had an electron in the fifth state. Actually, let's start with the third state. Let's say it was in the third state and a 5 eV photon came in. Well, it's going to be able to successfully absorb that in order to kick it up to this fifth energy state. Now it's in this excited state, and let's say it decides it's going to fall back down to the third energy state. If it's going to fall back down to that energy state, it's going to have to again emit a 5 eV photon. This is what I mean by the energies of the photons that this particular type of atom likes to absorb are going to be the same as the energies of the photons that this atom likes to emit. And again, these energy levels are unique to each atom. They depend on what type of element it is. They depend on if it's ionized or not. And they even slightly depend on what isotope we're looking at. So if we look at some light source and say, oh, it's giving off these particular energies of photons, or if we look at some spectrum and say, oh, these particular energies of photons are missing, that literally acts like a chemical fingerprint. This is how we can identify the composition of distant objects based on the light that they're giving off. Each kind of atom has different energy levels, different electron energy levels, and the spacings of those electron energy levels determines the photons of light that this thing will absorb or emit. So if we identify a sample and see which elements are absorbed and which wavelengths of light are absorbed and which wavelengths of light are emitted, we can use that to identify the element. So let's actually look at this. So let's talk about emission spectrum first. So I'm going to scroll. Let's scroll to the side instead. I think that'll be better in case I want to reference this. So let's talk briefly about emission spectrum. That's wrong. Basically, it's the situation where I have a thin gas that has been excited through being heated, or we're going to look at some cases where I run an electrical current through a gas to excite it, where we have an excited gas that will emit very, very specific colors of light. Excited gas emits specific colors, specific wavelengths of light. Wavelengths of light. When the electrons are going from those high energy states, because it's already been excited, when those electrons go from those high energy states and try to fall back down to lower energy states, we get a spectrum that looks like a few bands of light. So the spectrum looks something like this. We have wavelength and intensity. We see at very, very specific wavelengths, it's very, very bright. We see basically a dark background with a few bright bands of color. So dark background with some bright bands of color. And again, these bright bands of color, those are specifically associated with each of those energies of photons that this particular element likes to absorb or likes to emit. So let's look at a specific example of this. Okay, so what I have set up over here is this spectrum tube, and I've got my camera set up as well. So this is the view from the camera, again, looking at the spectroscope. And in here, we've got some hydrogen gas, and I'm going to run a current through it. So if I turn this on, then this is the spectrum that we see. There's some kind of background colors that not quite getting rid of, but hopefully you can see that there are some specific bands of bright light. So one right above 650 nanometers, another bright line here, bright line over here, one that's kind of hard to see, but it's there. There's some background colors. If it was a more finely tuned spectrum tube, this would be a fully dark background. But again, this gas, it glows with a very specific pink color. And when we look at this through the spectroscope, well, we can see those individual bands of colors. And again, these individual bands of colors correspond to very, very specific energy transitions inside of that hydrogen atom. So again, inside the hydrogen atom, it's just one proton in the very middle and one electron going around it. So it's the easiest one to analyze. And the red line corresponds to one particular energy transition that the electron can go through from a higher level to a lower level as that electron goes back down to a lower energy state. The kind of bright blue line that we see there, that's a different transition. The purple line that we see there, that's another transition. The one that, again, I don't know if we can really see it super well, but it's right around 415 or so. It's kind of in there. You can't really see it too well in this one, but that would be another one of these kinds of transitions. So if we see a thin gas of hydrogen that's been excited, it will glow and emit these very, very specific colors. So if we see these specific colors in some cloud of gas, we know that hydrogen is present in there. Let's look at another example of this. Okay, so I just switched the hydrogen tube out for helium. So this one actually has helium gas in it. We've got the view from the spectroscope set up, and this one, you'll notice, glows with a very different color. And this helium gas, it has different spectral lines. This helium, inside the atom, there are different allowed electron energy levels. Again, because it's got, more protons in it, it's got more electrons. Those electrons interact with each other in different ways. The electron energy levels, those are different than they were for hydrogen. And so this particular helium gas will give off different colors of light than what we had for the hydrogen gas. So if we see this particular set of colors, we know we're dealing with helium gas. And again, for every type of element, every type of ion, every type of isotope, they all have these slightly different colors, or sometimes significantly different colors, but they all have this unique set of spectral lines that we can use to identify when those elements are present in one of these thin excited gases. So again, the point of this part is for these emission spectra, we have some kind of excited gas where electrons have been pushed into these high energy states. And as the electrons try to fall back down to lower energy states, they're going to give off very, very specific colors of light. Again, for hydrogen, there are a set of transitions that are all associated with the spectral lines that actually produce photons that are in the visible part of the spectrum. But there are lots of other transitions that you can have, even for just hydrogen, which again is the simplest of the atoms. Some of them will produce spectral lines in the ultraviolet part of the spectrum. Some of them will produce spectral lines in the infrared part of the spectrum. Again, all different parts of the spectrum, even in the radio part of the spectrum, I don't think there's any elements that actually produce spectral lines in the X-ray part of the spectrum, at least as much. There are other effects that we can observe things in the X-ray part of the spectrum. But again, these kinds of spectral lines, it's not just the visible light that we care about. It's all of the different spectral lines that these elements can produce. So again, emission spectrum is when we have a thin excited gas and the electrons are going from high energy states to lower energy states. They're giving off very, very specific colors of light. And the spectrum ends up being this dark background with some bright bands of color. The wavelength versus intensity graph looks something like this. On the other hand, we can have what's called an absorption spectrum. We have absorption spectrum. These graphs look quite a bit different, because in this case, what we'll have is a spectrum that looks something like this. It'll have that overall shape, but there will be specific colors that are missing. So these downward little spikes at different locations. And to get this right, I'd have to erase these little parts, get something looking kind of like how it's supposed to. Basically, what the spectrum is going to look like is this rainbow of colors, but it's missing a few bands. So the spectrum is the rainbow, but with some dark bands. So this spectrum is quite a bit different looking than we had for the emission spectrum. And these absorption lines are occurring when light was going to pass through some thin cloud of gas, but that cloud of gas, it's really good at absorbing certain colors of light. So those particular wavelengths are removed from the spectrum. So here's the basic physical situation where you get this. If I have a source of thermal spectrum source, so a source of a thermal spectrum. Let me write that a little bit clearer. So that light is going in some direction, and that is the full, smooth, continuous thermal spectrum of light. And now I have some cloud of cold, thin gas. And as that light moves through that cloud of cold, thin gas, there are certain, again, wavelengths of light that the atoms in that cloud of gas are going to be really good at absorbing. and it's going to remove those colors of light from the spectrum. So by the time this light has made its way through, now we're going to get that spectrum that seems to be missing a few of those colors. We had the spectrum, the thermal spectrum before, but that light passed through this cloud of cold gas, and now some of those colors of light have been absorbed. So the hydrogen absorption lines, well, they show up again at the same wavelengths, and same photon energies as the hydrogen emission lines. And again, it's because, as we mentioned before, the same energies that a particular type of atom will like to absorb are the same energies of photons that that atom will like to emit. Again, this is one of the key ideas of spectroscopy. So if I have the same type of element, the hydrogen spectrum, hydrogen likes to emit light at the same wavelengths that hydrogen likes to absorb light. So those spectral lines will always match up with each other. So in either of these two situations, we can use the same set of spectral lines to identify that we're dealing with hydrogen or helium or iron or any other type of material. And again, the way that this is produced is we have this continuous, the source of a continuous spectrum, a thermal radiation spectrum, a solid, liquid, or dense gas. And as that light moves through this cloud of gas, those particular colors are going to be preferentially absorbed. But later on, after a very short amount of time, the light that cloud of gas absorbs, it's going to re-emit that light, but generally in a random direction. So this cloud of gas is absorbing some of this original beam of light and then re-emitting it in a different direction. So it seems to disappear from the original absorption spectrum and then show up if you're just looking at this cloud of gas from the side. It's now an excited cloud of gas because it's been excited by the light that has been irradiating this cloud of gas. I think this little animation is kind of the best at demonstrating what's happening. So let's say this is an atom that's really good at absorbing orange light. So it absorbs that orange light. All of the colors are being given off by this original continuous source of light. But when all of those colors of light end up going through this atom, we'll wait for this to reset. When all of these colors of light go through this atom, it preferentially absorbs the orange light. So if we're looking through that cold cloud, we see this absorption spectrum where, oh, that band of color is missing. On the other hand, if we're looking over here at where that missing band of color was re-emitted in, the direction that missing band of color was, sent off in, that's going to be our emission spectrum. So again, I do recommend, having a double check through this video to kind of see what's happening, how we're producing this absorption spectrum, how we're producing this emission spectrum. Again, that continuous thermal radiation spectrum gives us lots of different wavelengths of light to choose from. And as that source of that thermal spectrum moves through this cloud of colder gas, well, all the different wavelengths and energies of light are there. Whichever one this cloud of gas is good at absorbing, it's going to take those out of the spectrum. So again, this kind of overview allows us to identify how each of these types of spectra are produced. Continuous spectrum, it's just if I have a solid, liquid, or very dense gas that's producing this continuous spectrum, that's going to be the thermal radiation that we talked about before. If this spectrum shines through a colder cloud of gas, that cloud of gas is going to absorb certain wavelengths of light. And if I'm looking from this direction, I'm going to see this absorption spectrum. The wavelengths of light that this cloud of gas absorbed, it's going to tend to re-emit those wavelengths of light in a random direction. So if you're looking at this cloud of gas from the side, it's been excited by this nearby star or whatever this object is, and now we see that emission spectrum. So we're going to be looking at all of these different kinds of spectras throughout the course. Let's just see how they all are related to the sun in some way. So in the kind of lower down layers of the sun, inside the photosphere itself, where the gases are much denser, the sun is actually producing this thermal radiation spectrum, this kind of smooth band of colors. But in those underlying layers of the photosphere, like kind of deeper into the photosphere, that light has to make its way out through the colder layers of the photosphere, which is approximately a 500-kilometer thick layer of cooler gases that absorb certain wavelengths of light. So we get that effect of, oh, the interior of the sun is this hot, dense gas. It's producing this thermal spectrum, but that light has to make its way out of the sun. And it's got to pass through those cooler layers of the photosphere before it does that. So it's going to make an absorption spectrum. However, if you look at the outer part of the sun's atmosphere, what we call the corona is made up of thin gases that have, in a way that we don't really understand yet, has been heated to literally millions of Kelvin. We are going to talk about the properties of the sun and the properties of the sun's atmosphere, this corona. But right now, there's some way that magnetic energy from the sun is driving these outer layers of the sun's atmosphere to get very, very hot, millions of Kelvin. And that solar corona produces an emission spectrum. It's a hot, thin gas. And if you look at the light just from that corona, you're going to see that those individual bands of color on a dark background, one of those emission spectrums. This is a high-resolution version of the sun's spectrum. And there are literally tens of thousands of absorption lines that have been identified in the spectrum of the sun. And this is just looking at the visible spectrum. This isn't even looking at the infrared part of the spectrum, the ultraviolet part of the spectrum, where there are other spectral lines as well. And again, each of these sets of spectral lines really acts like a barcode and identifies what type of material was actually producing these spectral lines. We've got the spectral lines associated with all sorts of elements. Again, we're going to talk about this more when we talk about the properties of stars and how much information is encoded in here. But at least for now, we've got these different kinds of spectra, these emission spectrum, absorption spectras, how they're produced, both in terms of what's going on inside of the atom, again, how these electrons are changing between energy levels, and on kind of a larger scale of how, if I have a thin excited gas, I'm going to make an emission spectrum. If I have a cold gas in front of a hot, dense source, I'm going to make one of these absorption spectras. We know how to make these spectras. We can use them to identify very particular elements. Those are some of the key properties of spectroscopy that I wanted to emphasize for this particular session.